Bismillahirrahmanirrahim. Assalamu alaikum warahmatullahi wabarakatuh. So section 3.7 is talking about derivative of inverse functions. In this section we have two aims. The first one, we need to determine the relation between the continuity and the differentiability of f and f inverse. The second one is to derive the derivatives of inverse trigonometric functions. We need to know also, this is from section 1.5, we need to know that what is one-to-one function, what is the relation between f and f inverse, and the inverse of trigonometric function. So let us start by theorem 371, which is talk about the continuity of the inverse function. So if f is continuous, its inverse also will be continuous as well. So let us see this theorem. It says let f be a continuous one-to-one function on its domain x, then f inverse is continuous on its domain. So in brief, if f is continuous and one-to-one, its inverse also will be continuous. So the f inverse will be continuous if the function f continuous and one-to-one function. How to know that a function is decreasing or increasing? There is two ways to know the function is increasing or decreasing. Let us see this graph. Take the interval, consider the interval from A to B, and you have two values, x1 and x2, where x1 is less than x2. The value of x1 is here, fx1, and the value of x2 is here, fx2. If you compare the value of fx1 with the value of fx2, you will see that fx1 is less than fx2. So your function is increasing on the interval I1, where I1 is the interval from A to B. So the function here, it is increasing since x1 less than x2 and fx1 less than fx2. What about the function when it is decreasing? So let us consider the second interval from C to D, which is I2. Let us take x3 and x4, where x3 is less than x4. If you evaluate fx3, it will be here, and if you evaluate fx4, it will be here. So if you compare fx3 with fx4, you will see that fx3 is greater than fx4. So your function is decreasing on the interval I2, and this will be for all the value in this interval I2. Whenever you take x3 less than x4, then you compare fx3, it will be greater than fx4, so you conclude that your function here is decreasing. So this is the first way. The second way, you compare the derivative or the tangent line. So for the interval I from A to B, the derivative of the function at x1 or the tangent line looks like this one, which is positive. Also the derivative at x2, which is the tangent line, looks like this one, which is positive. So here your tangent line is positive, so that means your function is increasing. On the other hand, you have the interval C to D, which is I2. If you find the derivative of this function or the tangent line at x3, it will look like this line, and at x4, f prime x, or the derivative will be like this one, which is negative for both of them. So since here the derivative is negative, so that means your function is decreasing. So you know that your function increasing or decreasing either by choosing 2 points in this interval and compare between the value of the function at these 2 points, or you check the value of the derivative. If it is positive, that means your function increasing. If it is negative, that means your function is decreasing. How to determine that f inverse exists? So this will be in theorem 372. Are all function has an inverse function? Let us see. Let f be a continuous function and increasing on an interval a to b, then f inverse exists and is continuous increasing on fa, fb. So if f is continuous and increasing on the interval a to b, that's mean f inverse exists and it is continuous and it is increasing on the interval fa to fb. You can replace this increasing by decreasing. So if your function f is continuous and decreasing, that means f inverse exists and it is continuous and it is decreasing on the interval fa, fb. Why we choose here the interval a to b and here fa and fb? Here because the domain of the function f is the range of the function f inverse and vice versa. So the range of the function f will be the domain of the function f inverse. So that's why we write here fa, fb. So when your function f inverse exists, if your function f continuous and it is either increasing or decreasing. How to show that f inverse is differentiable? Let us see this by Theorem 373. Suppose f is a differentiable function on an open interval a to b. If either f prime x greater than 0, so that means your function is increasing on the interval, or f prime x less than 0, that means your function is decreasing on the interval, then f is 1 to 1. Moreover, f inverse is differentiable for all x in the range of f. So in brief, if you have our function fx is differentiable and it is either increasing or decreasing, which is f prime x greater than 0 or f prime x less than 0, then we have two results. The first one, f is 1 to 1. The second one is f inverse is differentiable. So if your function f is differentiable and either it is increasing or decreasing, the result f is 1 to 1 and f inverse also will be differentiable. Now let us see example 1. Prove that f of x is equal 10x cubed plus 8x plus 12 has an inverse. We say that, so here we are looking for the existence of f inverse. We will use the theorem 372 because this theorem is talking about the existence of f inverse. So we say that any function has an inverse if it is continuous and it is either increasing or decreasing. So let us apply this in this example. Fx is equal 10x cubed plus 8x plus 12. This function is a polynomial and we know that any polynomial is continuous. So the first one is satisfied. Then we need to check if this function is increasing or decreasing. So how do we know that? First we will find the derivative. F prime x is equal 30x squared plus 8. This function is greater than 0 for any value. Why? Because if you take any value here, for example, let us take 1. 30 multiplied by 1 plus 8, this one will be positive. If you take any other number which is negative, for example, minus 1, 30 multiplied by minus 1 square will be 30 plus 8, so 38 is greater than 0. So once you substitute any value here, you will get always positive value. So that means fx is increasing on the interval minus infinity to infinity. So by the theorem 372, we conclude that f inverse exists. So f inverse exists because this function is continuous and it is increasing. Another example, which is example 2. Let fx is equal x squared plus 1, where x greater than or equal to 0. Find f inverse function and its derivative. Then we need to find f prime 2 and f inverse, the derivative of f inverse at 5. So let us do part 1. Find f inverse function. So we have f of x is equal x squared plus 1. We can replace f of x by y, so it will be y is equal x squared plus 1. To find f inverse, first we need to rewrite this function as a function of x. So let us move this one with y, so it will be y minus 1 is equal x squared. To solve it for x, take the square root for both sides. So square root of y minus 1 is equal x. So for sure this one is positive or negative, but since here we consider x greater than 0, so we'll take just the positive one. So now to rewrite f inverse, replace x by f inverse x, replace y here by x. So we'll get f inverse x is equal square root of x minus 1. Part B, we need to find f prime 2 and the derivative of the f inverse at 5. So in the previous, we find what is our f, we are given what is fx, we find what is f inverse x, which is square root of x plus 1. So at x is equal to, we need to find what is f2. f2, we go to the function f, replace any x by 2, so it will be 2 squared plus 1, which is 5. And f inverse 5, so we go to this function f inverse, replace any x by 5, we will get square root of 5 minus 1, which is 2. So then we need to evaluate the derivative. We need to find f prime 2 and the derivative of f inverse at 5. So f prime 2, the derivative of fx is equal to x. And the derivative of f inverse, so we need to differentiate this one. It will be 1 over 2 x minus 1 power minus half, which is 1 over 2 root x minus 1. So the value of the derivative of f, or the value of the derivative f, which is 2x at 2 given by 2 multiplied by 2, which is 4. And the value of this derivative at 5 is equal 1 over 2 multiplied by square root of 5 minus 1. It will be 2, so 2 multiplied by 2, 4. So the derivative of f inverse at 5 is equal 1 over 4. Now, if you compare the derivative of f prime at 2 is equal 4. The derivative of f inverse at 5 is equal 1 over 4. So the relation between their derivative is reciprocal. That means f inverse prime at 5 is equal 1 over f prime 2. Or f inverse prime at 5 is equal 1 over f prime f inverse 5. Why we choose here the derivative at 2, whereas we choose here derivative at 5? Because we know that here the domain of this function 2 is in the domain of f. So we need to find the derivative at the domain, so f prime at 2. But for this one, if the point 2, 5 is in f, that means the point 5, 2 is in f inverse. So 5 here is in the domain of f inverse. So that's why we evaluate the derivative of f inverse at 5, not at 2. So the relation between the derivative of f and the derivative of f inverse is given by the next relation. So suppose that f is differentiable on an interval I and f prime is never 0 on I. If f has an inverse, which is f inverse on I, then f inverse is differentiable at a number x, and the derivative of f inverse is given by 1 over f prime f inverse x. Why we need to use this relation? Because we don't have to find every time the f inverse then we find the derivative. No. And sometimes you cannot evaluate the inverse of any function because it takes long time or it's hard to do it. So that's why we use this rule to find the derivative of f inverse. So if f is differentiable and the derivative is never 0 for any x, and f has an inverse, we conclude that the derivative of f inverse is given by 1 over f prime f inverse.